These are our Chapter 18 electrochemistry notes. Our outline is Introduction, Galvanic Cell, which introduces us to cell diagram and line notation and the hydrogen electrode. We have potential, delta G and K, those are from previous chapters, the Nernst equation, and the electrolytic cell. So the introduction, electrochemistry, our chapter title, is the study of the exchange of chemical and electrical energy. We study this topic, this exchange of chemical and electrical energy, using one of two types of cells. They are both electrochemical cells. So electrochemical cells come as two types. The galvanic cell, which could also be called a voltaic cell, is also a battery, and in it, chemical energy is converted to electrical energy. For example, take the reaction Mg plus Cl2 forming MgCl2. This is a spontaneous reaction. That is to say, delta G is less than 0. Delta G, recall from the last chapter, also describes the maximum amount of work that a system can give us, that a process can give us, if the process is spontaneous. And we're going to use that topic again. MgCl2 is found as such in nature. That's the way magnesium wants to exist if it's hooked up to chloride. We can tap into the chemical energy present in Mg and Cl2 and convert it to electrical energy. From this process, we get electricity, that is a battery. This kind of process is done in a galvanic cell. So a galvanic cell implies spontaneous. It implies energy is given off. The maximum amount, W max, is delta G. That's one kind of electrolytic cell. The other, or electrochemical cell, the other kind is called an electrolytic cell. It's kind of the opposite to the galvanic cell. In an electrolytic cell, energy is converted, electrical energy is converted to chemical energy. That is to say, we get materials out of it. For example, if we take the way magnesium is found in nature when hooked to chloride, magnesium chloride, MgCl2, and we make Mg plus Cl2 from it, we have to supply energy. That reaction is not spontaneous. Delta G is greater than 0. The minimum amount of energy we would have to supply, W min, would equal delta G. So we must supply energy. We supply it usually in the form of electrical energy in order to make the products magnesium and chlorine. So we use an electrolytic cell to get materials. We will talk about a galvanic cell, the galvanic cell, for a while, and then eventually talk about an electrolytic cell toward the end of the chapter. So in a galvanic cell, as we talked about before, chemical energy is converted to electrical energy. It's a spontaneous process. Delta G is less than 0. If we were to take a solution, if we were to take a zinc, let's say nitrate solution, so we have Zn2 plus in solution, along with the spectator NO3 minus, and put a piece of copper metal in it, we would find that we get no reaction. We could wait a while and we still would not get the zinc 2 plus and the copper metal to react. If, on the other hand, we put a copper solution, copper 2 plus solution into a beaker, it would be, for example, copper sulfate or maybe copper nitrate. In there, we have Cu2 plus whatever the spectator anion is. It would be a blue solution. And we stick a piece of zinc metal into it. We would find that the blue color starts decreasing. We would find we start getting tarnish forming onto the zinc metal. So if we look at the two possible reactions, the first one, zinc 2 plus copper yielding zinc plus copper 2 plus, delta G is greater than 0. We will see that the potential, which is that squiggly E equaling to negative 1.10 volts, we will talk about that later. The fact that delta G is greater than 0 corresponds to a potential being negative. Okay, so that reaction doesn't occur. We would see that if we did that reaction. If we tried to set that one up and make something happen, nothing would happen. On the other hand, that other reaction where we have zinc plus copper 2 plus, we do get a reaction. And the products are zinc 2 plus copper metal. The delta G is less than 0, or we will find later that the potential is positive. So copper forms on the zinc electrode and the blue color of the solution decreases. Here would be on the left, the initial setup using copper sulfate in this case. And that would be after a period of time. The blue color goes down because the amount of copper 2 plus in the beaker has decreased. And the zinc 2 plus is colorless, so we won't see evidence of that one by just colors. But the copper solid that forms is plating onto the zinc metal, and you can't really, given everything there, see the typical copper color of it, but it would have that if we let it go long enough, we had enough zinc 2 plus, and we got kind of a layer of the copper plating onto the zinc, we would be able to polish it and it would start looking more like typical copper metal. So here's some details of what's going on. The electrons from the zinc, so here's the zinc metal, that diagonal piece of metal in there. A zinc atom becomes zinc 2 plus by losing 2 electrons. Those 2 electrons go to a copper 2 plus on the piece of zinc metal, because metal, you know, is a good conductor of electrons. It goes on there and it forms a copper atom, which then plates onto the zinc metal. The half reactions are Zn forming Zn2 plus 2 electrons, and copper 2 plus 2 electrons forming copper metal. The zinc reaction is oxidation, and it's the oxidation half reaction. Oxidation states, remember that term, oxidation number, oxidation states. In our case, that would reflect the charge. The zinc as an atom has no charge. The zinc as zinc 2 plus has the 2 plus charge, so its oxidation state is 2. The copper reaction is a reduction reaction. Electrons are being taken on. It's the reduction half reaction. The oxidation states there are for the copper atom 0, for the copper 2 plus 2. If we separate the two half reactions, by that I mean into separate compartments, maybe separate beakers, then we can tap into the energy involved in zinc losing 2 electrons and copper 2 plus gaining 2 electrons. Perhaps if we had a good voltmeter, so we connect the pieces of metal, what we call electrodes, the piece of zinc, the piece of copper. Now, copper is not a reactant, but we have to have some kind of a conductor of the electrons. The electrons need to flow from the zinc metal, where zinc 2 plus is formed, on the left side, through the zinc metal to the copper metal, through, in our case, this voltmeter, and then into the copper 2 plus solution, so that a copper 2 plus ion can take on those 2 electrons and form copper, the atom. So if we had a voltmeter to measure kind of like the drive to make this happen, we would see initially a voltage, but it would stop very quickly. In fact, we probably would never see a voltage. But let's pretend for a moment we saw a voltage. It stops, though, given our setup in that diagram, because as zinc 2 plus forms, the left compartment would start becoming more positively charged. Nature doesn't just do that. And as copper 2 plus gets used up, the right compartment, the copper compartment, would be getting more negatively charged as we get rid of the cations in it. And that would stop the process. So what we need to do is have a way to keep the 2 solutions neutral. The ion count needs to be such that each compartment is neutral. So we can achieve that with a salt bridge. And what that salt bridge does is it allows for ions to move from one side to the other, keeping the 2 solutions neutral. And this would complete the circuit. So when we have this copper zinc setup, we have what's called a Daniell cell, and it is just like the diagram above, except with that salt bridge inserted. So the copper 2 plus concentration on the right side decreases, so we need to remove anions. So imagine NO3 minus moving out of there, flowing toward the left. And as zinc 2 plus builds up in the left compartment, we need more anions over there to balance it. So that's what the salt bridge does. Keeps the solutions neutral. So the process, the reaction that is there, the net reaction, the zinc plus copper 2 plus forming zinc 2 plus copper, can continue happening. These items that keep the solutions neutral come as 2 types. One is the salt bridge, just like what we have talked about already. It's shown in A on the left side. The other one is a porous disc that allows ion movement as needed to keep solutions neutral. That's in diagram B. This diagram with that voltage of 1.10 volts is showing the Daniell cell setup. So in the left compartment, we have the colorless zinc solution. We have the piece of zinc. There we have the salt bridge going over to the blue solution, the copper solution, and we have the piece of copper. You see that orangish looking metal there. The black lead and the red lead, those are what are connecting to the voltmeter and allowing for current to flow from the zinc side to the copper side. And going through the voltmeter allows us to measure what that potential is, where the potential is the push of electrons to leave the one side and the pull of the electrons to go to the other side. And then here's another diagram of the same setup, giving more details. So it's showing the electron flow direction, it's showing the voltage. So it goes from the zinc side to the copper side. The side where oxidation occurs, in our case the zinc side, that compartment is called the anode, and the piece of metal is often called the anode electrode, or simply the anode. the compartment where reduction is occurring, in our case the copper side, that is called the cathode. The piece of metal is called often the cathode electrode or just the cathode. So we're seeing the solutions that we have present there. In this diagram, we have a porous disk keeping the two sides solutions neutral. In the diagrams below, you can see zinc, the atom, forming zinc 2 plus the ion, giving up 2 electrons. And you can see those 2 electrons coming in, interacting with a Cu2 plus to give Cu the atom. Okay, so a little bit more of what we just talked about. The electron conducting material is called an electrode. The electrode compartment where oxidation occurs is called the anode. And the electrode compartment where reduction occurs is called the cathode. And this is true for a galvanic cell. This is also true for an electrolytic cell. Since electrons leave the cell at the anode, it's defined as the negative terminal or negative electrode. Since electrons enter at the cathode, it is the positive terminal. Think of electrons wanting to go toward the positive, electrons wanting to move away from the negative. Okay, so a summary of what we talked about. Anode, oxidation, negative electrode, cathode, reduction, positive electrode. This plus and minus connected to the anode, the cathode, this is true for galvanic cells. It turns out electrolytic cells have the opposite signs associated with them because that's a reaction we're having to force to go in the way it does not want to spontaneously go. Okay, a new term is line notation and cell diagram. Line notation is a shorthand way of basically summarizing most of the important details of what we see in a cell diagram. A cell diagram is kind of like that picture we're seeing there with all the details. Line notation to us, once we are familiar with how to use it, is a summary of that. So the arrangement of electrodes in a galvanic cell is summarized by a cell diagram, which is built up from line notation. Line notation. In a cell diagram, the anode information is written on the left, and the cathode information is on the right. The anode electrode is written on the far left, and the cathode electrode on the far right. Phases are separated by a vertical line, and the salt bridge is represented as a double line, looking kind of like the salt bridge. Okay, so what that comes down to is the anode material is written first, and the cathode material is written last. So the line notation of this cell, of the Daniell cell, of the zinc copper cell, would be Zn solid. That is part of the anode. All the anode info is on the left, and that is also the electrode. Zinc as part of the overall reaction, yes, but it's also the electrode. And then we have a bar because zinc, the solid, is a different phase from zinc 2 plus, the aqueous solutions. We have Zn solid line, Zn2 plus, that's part of the anode, aqueous. Then we have the double bar for the salt bridge. Now we come to the cathode side, and we put copper 2 plus aqueous, bar, and then copper solid. Lastly, we have copper solid because it's the electrode, and the cathode electrode is written on the far right, whereas the anode electrode on the far left. So once we're used to that line notation, it gives us all the details of that cell diagram, of that battery, the Daniell battery, the Daniell cell. Okay, some new terminology also is copper 2 plus / copper. That's what's termed a redox couple, and it's typically written in the reduction direction despite what occurs in a particular cell. So that's a redox couple in the Daniell cell. The other redox couple is zinc 2 plus / zinc. Notice, going back to the line notation of the Daniell cell, notice that you can kind of picture the reaction and the direction in which it occurs looking at this notation here. We have Zn plus copper 2 plus forming Zn2 plus copper. Okay, from the line notation, we know that oxidation occurs at the zinc 2 plus zinc redox couple, and reduction occurs with the copper 2 plus copper redox couple. We know that because we always put the anode information on the left and the cathode information on the right in line notation. Notice that the cell diagram we have here with the voltmeter and salt bridge, notice there we also have the zinc compartment, the anode compartment on the left, and the cathode compartment on the right. But as I write in the small text paragraph to the right of that cell diagram, I usually draw the anode on the left side, but it could be drawn on the right side. That is, when I draw a cell diagram, I usually do put the anode compartment on the left, the cathode compartment on the right, just because that's the way it has to be in the line notation. But it could easily be the other way around in the cell diagram. But when we draw line notation, that always is anode on the left, cathode stuff on the right. Okay, now we'll get into what we call the hydrogen electrode. And it's very important in electrochemistry, as we'll see as we go on. So let's look at this reaction. Zinc plus 2 H plus yielding zinc 2 plus H2. That's a spontaneous reaction. And if we set it up, we might set it up as the cell diagram here shows. So we get our zinc electrode in a compartment and the zinc 2 plus solution. We have that external wire connecting to a voltmeter if we want to measure the potential involved. Over on the right side, that would be the cathode side, we have what's called the hydrogen electrode. There we have the reaction occurring where H plus is taking on electrons to give us H2. Now, notice that that half reaction involves H plus and H2. It has no piece of metal. We need that piece of metal in order to allow for the electrons to flow, to be the conducting material. What we often will use is a piece of platinum metal. Platinum is, it's pretty unreactive because we don't want that reacting in our reaction. It's not part of our overall reaction. It's just pretty inert. It has a very high melting point. It's just not going to really change any. Okay, so what we have here in that cathode compartment is we have the hydrogen electrode. That involves a source of H2 gas, and it's sitting in a solution involving H plus ions. And there we have the platinum electrode. Hydrogen is useful. Hydrogen can be oxidized. Electrons can be removed from H2, or hydrogen can be reduced. Electrons can be added to H+. Since H2 and H+ don't contain a metal, a chemically inert metal is needed as the electrode to accept or remove electrons. So just what we were talking about earlier. Platinum is customarily used as the electrode due to its high melting point, 1768 degrees Celsius, and it really does not want to be oxidized. It does not want to be involved in the reaction. It has, as it turns out, a very high potential. So the inert metal that's used, usually platinum, only transfers electrons to or from the hydrogen and is itself not oxidized or reduced. So the platinum is placed in that hydrogen ion solution and H2 gas is bubbled over it. This whole arrangement is one electrode, and it's the hydrogen electrode. Okay, so what would be the line notation of the reaction we had from above? Let me go back to it. Okay, so there it is. So why don't you take a moment to write that reaction down. We have zinc forming zinc 2+, that's occurring at the anode. We have H+ forming H2, occurring at the cathode. And then we have that platinum metal acting as the cathode electrode. Okay, so what would be the line notation? So take a moment to write out what that would be, or come back to that later on your own and do it. So it would look like this: zinc solid / zinc 2+, that's what's occurring at the anode side. Then we have the salt bridge. Then we have H+ bar, H2 gas. The reason we have a bar between those is because the H+ is aqueous, the H2 is a gas. Now we follow it with the bar and then platinum solid, because that is the electrode, the cathode electrode. Okay, so we have a reaction here, H2 plus 2 Fe3+, forming 2H+ plus 2 Fe2+. So we have a cell composed of that reaction. What is the line notation of this cell? So maybe pause the video to come up with that, maybe come back to it later. All right, our next topic is potential, delta G and K, the equilibrium constant. The energy released by the redox reaction as electrons spontaneously travel through the wire can be used to heat the surroundings if the circuit contains a heater, or to do work if the circuit includes an electric motor, like that in a blow dryer, or to produce light if the circuit contains a light bulb, or do other things, whatever takes energy that electrical energy could work for. The energy released in the cell depends on the pushing and pulling tendency of the electrons involved in the redox reaction. If the oxidation reaction readily releases electrons and the reduction reaction readily accepts them, then the electrons will be pushed and pulled through the circuit vigorously, and the reaction can provide lots of energy. This pushing and pulling tendency of the cell is measured as the potential, the difference in volts between 2 points in the cell. So that is the potential. That's what the squiggly E is used to symbolize. I just refer to that as E. So it is symbolized with the Greek symbol xi from the Greek alphabet, a script E. The SI unit, the metric unit of potential, is the volt, a capital V. This potential can also be called the electromotive force, the EMF, or voltage. The greater the cell potential, the greater the energy that a given number of electrons can release as they travel between electrodes. A high potential signifies that the reaction has a strong tendency to generate a current of electrons. the cell potential for the Daniell cell, for the zinc copper cell, is 1.10 volts, and that would be at standard conditions. That's what that not implies. Standard conditions, 1 molar concentrations, 25 degrees Celsius, 1 atmosphere pressures if gases are involved. For a galvanic cell, a spontaneous reaction cell, the potential is greater than 0, it's positive. Okay, so the potential in volts is equal to the energy in joules involved in the reaction divided by the charge, where the charge, the metric unit for charge is a coulomb. Now we're used to the charge of an electron being -1, but that's a relative quantity. The charge in coulomb units is equal to, well, negative 1.602 times 10 to the minus 19 coulombs per electron. If we multiply that by Avogadro's number to determine the charge per mole of electrons, we get that Q is equal to 96485 coulombs. This quantity is referred to as Faraday's constant. We will see that later. So the Faraday's constant is 96485 coulombs per mole of electrons, and it is symbolized F, capital F. Alrighty, so what we have is, if we rearrange potential equaling energy per charge in terms of energy, we have energy in joules is equal to charge in coulombs times potential. What that comes down to, if we just look at units, is 1 coulomb volt equals 1 joule. 1 coulomb volt equals 1 joule. Alrighty, so we have energy equals charge. By the way, Q is a common symbol to use for charge. Energy equals charge times potential. That would be electrical energy. Or we could write for electrical energy E equals Q times psi. We also have gravitational potential energy, which is equal to E equals mass times GH. Now, gravitational potential energy. Imagine we have water on the top of a cliff, and it is flowing over the cliff. That is what hydroelectric plants hook into to take the potential energy of that water up on the top of the cliff of height h and convert it to electrical energy down at the bottom of the cliff. And I'm trying to, in this example here, equate energy and potential to emphasize the difference between the two, because I have found it's a common error for students to kind of get mixed up between potential, that script E, and energy, E. Alrighty, so we have that mass of water, M, at the top of the cliff. The cliff is at a height h from the bottom. When we take a quantity of water of mass m and drop it down that cliff of height h, the energy is equal to m, the mass of it, times g. G is a constant. It's constant due to gravity, so it's just a number, times the height of the cliff. That's how we get energy out of the process. We know if there's no water flowing over that cliff, we get no energy. We also know if there's no cliff, we get no energy. We have to have, of course, the body of water, M, and the cliff of height, H. Now, whether we have a mass of water going over the cliff, you could say that we have like the potential to get energy out of it if only we had water up at the top of it. The potential of that cliff we could say is like GH. Going to electrical energy, unless we have both charge flowing and a potential, we have no energy out of the battery. We have to have current flowing, we have to have a potential. The product of the two is the energy involved. It's not the potential to have that happen, it's current flowing given that potential. Okay, so potential and energy are different. They're very related, but they're different. Just as energy and GH are related, but without that body of water flowing, we get no energy from that waterfall. Okay, so we have to keep that in mind as we go on. So we have from earlier that delta G is equal to the maximum amount of work that we can get out of a spontaneous process. We have a negative sign in there because from the perspective of the system, its energy has decreased because work has been done by the system. Electrical energy, we have energy, or we could say W for work, is equal to charge times the potential. That is to say, delta G is equal to minus QE. Okay, now looking at just the Q part of that, the electrons involved, we have in a given reaction, we have so many moles of electrons involved for moles of, we could say, reaction, like zinc forming zinc 2+. We have for every zinc, for every like mole of reaction, we have 2 moles of electrons involved. And those 2 moles of electrons go to the copper 2+ to give us a mole of copper. So we have a certain moles of electrons per moles of reaction, but we want the charge. So we multiply by Faraday's constant, which recall from higher up on this page, that is 96485 coulombs per mole of electrons. So notice that mole of electrons cancels out and we calculate the charge involved. So often moles are referred to with the symbol N, so we replace moles of electrons per mole of reaction by N. We replace the 96485 coulombs per mole of electrons with F. And we have delta G is minus NF times the potential. That's how we can calculate the amount of energy, free energy change involved in a reaction. Okay, so for the Daniell cell, the reaction is zinc plus copper 2+ yielding zinc 2+ plus copper. If you're given that the potential at standard conditions is 1.10 volts, then you can calculate delta G naught. So delta G naught is minus NF E naught, which is equal to minus 2, because we have 2 moles of electrons transferred from the anode side to the cathode side. So we have 2 moles times the Faraday's constant times the potential. Now realize that N is totally technically moles of electrons per moles of reaction. So we have the moles of electron part canceling out, and we get that delta G naught, standard conditions, is equal to negative 212,000 joules, or negative 212 kilojoules. Okay, our next page. So there's the reaction. Zinc plus copper 2+ forming zinc 2+ plus copper. The potential of 1.10 volts at standard conditions. The reaction occurring at the anode, so the potential sub A is zinc plus Zn2+, or zinc yielding zinc 2+ plus 2 electrons. the reaction occurring at the cathode is copper 2 plus 2 electrons forming copper. So we could symbolize each of these half reactions with a potential, so EA and EC. Our overall reaction is zinc plus copper 2 plus forming zinc 2 plus copper. So the overall potential would be the potential at the anode plus the potential at the cathode. In that diagram, we see if we have an analog kind of meter, we have a certain potential for the anode to occur, a certain potential for the cathode to occur, and the overall potential would be the sum of the two. If we knew EA and EC, we could mix and match many different redox couples. This is done using the hydrogen electrode as the reference. Its value is set to 0, and all other half reactions are set relative to this choice. So it's the reference, kind of like you know how long a meter is, that's a reference, and we make all measurements based on that when measuring in meters. Okay, so we use the hydrogen electrode as the reference, and we have the hydrogen electrode could be oxidized, it could be reduced, depending on the other redox couple it's matched up with. It is set to 0 no matter whether acting at the anode or at the cathode. Okay, so let's, in our example here, hook it up with zinc. And there's the overall reaction, zinc plus 2H plus yielding zinc 2 plus H2. The overall potential, let's say we measured at standard conditions to be 0.76 volts. And the zinc is being oxidized, so we have at the anode, so the EA describing that potential, that reaction would be zinc yielding zinc 2 plus 2 electrons. And at the cathode, the reduction half reaction in this case is 2H plus 2 electrons yielding H2. We have the overall potential, E naught at standard conditions equaling EA plus EC. We put in E naught to be what we measured, 0.76 volts. That's equal to EA plus 0 because that's our reference for the hydrogen electrode. That means that EA is equal to 0.76. Now, that's written for zinc as an oxidation half reaction, which is what it's doing in this particular cell. If we were showing it as a reduction half reaction, then we would reverse the reaction, so write it as zinc 2 plus 2 electrons yielding zinc, and we would have to change the sign of the potential, so we would have it to be negative 0.76 volts. So in a similar fashion, reduction potentials for many substances were determined and are given in standard reduction potentials tables. So here is the standard reduction potential table in your book. It's at standard conditions, 25 degrees Celsius, 1 molar concentrations, 1 atmosphere pressure. So it's up at the top, we have F2 plus 2 electrons yielding 2F minus. We see that that is the largest potential on this list of standard reduction potentials. It's positive, that means it very much wants to go. F2 very much wants to be reduced. It wants to take electrons. In fact, it can take electrons from anything below it on this table. Go to the other side of the table, the very bottom, Li plus an electron yielding Li. That has a very negative potential. What that means is lithium very much wants to form Li plus, the ion. by giving up an electron, very much wants to be oxidized. Its potential to be oxidized would be 3.05 volts. And it will give electrons to anything above it. It will reduce anything above it in that table. Alrighty, so here's an example. Calculate the potential and delta G at standard conditions for the reaction F2 plus 2 AgI yielding 2F minus plus 2 Ag2 plus. So in our table, what we would find is Ag plus yielding Ag2 plus an electron that has a potential of negative 1.99 volts. And we would find that F2 plus 2 electrons yielding 2F minus has the potential to be 2.87. Now, actually, before we go back to those two half reactions, notice in our overall reaction, fluorine is being reduced. It is taking on electrons. And silver is being oxidized. It is losing electrons. The silver is what is the half reaction that's going to occur at the anode, and the fluorine half reaction is going to be occurring at the cathode. So what I did was I found, looking back at the table, I found the potential for the silver reaction. That's the second one, and I flipped it around because in this case it's being oxidized. I had to change the sign of the potential. And the fluorine reaction is the one above it, and indeed in our situation here it is being reduced, so we write the reaction just as it is. We don't change the sign of the potential. So that's where we came up with those two half reactions and their corresponding potentials, E sub A, E sub C. Now, in our case, we have two Ag plus involved. We have two Ag2 plus involved in order to get the two electrons that will then be taken by the F2. But notice that the potential is still negative 1.99 volts. It is not doubled. And that's because there is, as I tried to say earlier, a difference between potential and energy. The potential is just the drive of the one to lose electrons and the drive of the other one to gain electrons, like to push those electrons away, to pull the electrons in, kind of like the cliff. Its height is still h no matter if a little bit of water flows or a lot of water. The potential is given by GH. It's not going to change. The potential for the electrical considerations is the same idea. It has to do with the pushing and pulling tendency of the two half reactions. So we don't multiply that by 2. Okay, so we have the overall potential is EA plus EC, or negative 1.99 plus 2.87 volts, giving us the potential at standard conditions of 0.88 volts. So we were also asked to calculate delta G naught, so we have delta G naught is equal to minus NFE naught, which is negative 2 moles of electrons per mole of reaction, because we have 2 moles of electrons involved. 2 moles being lost by the 2 Ag plus, 2 moles being taken on by the F2. We have times Faraday's constant, 96485 coulombs per mole of electrons, times the potential, 0.88 volts. And because Coulomb volt is equal to joule and moles cancel out, we end up with our unit being joules, number being that negative 170,000 volts, joules, or we have the delta G naught is equal to negative 170 kilojoules. So in our last chapter, we had the relationship delta G naught, so standard conditions, is equal to minus RT ln of K. Now in this chapter, we have delta G naught is equal to minus NF E naught. So we can equate those two. So we have minus RT ln of K is equal to NF E naught. And by the way, R is the universal gas constant, and T is temperature in Kelvin. K is the equilibrium constant. Okay, so we can do some rearranging. We get ln of K equal to NF E naught over RT, or we get K is equal to E to the NF E naught over RT. So if we know E naught, we can calculate what the potential, the equilibrium constant would be for that reaction. So working with that same reaction, where we have the potential of 0.88 volts, we can calculate K. So we take our new equation for K equals E to the NF E naught over RT, put in all of our terms, N being 2 moles of electrons per mole of reaction, F being 96485 coulombs per mole of electrons, the potential being 0.88 volts or 0.88 joules per coulomb, dividing by R, 8.314 joules per mole Kelvin, dividing by the temperature, assume 298 Kelvin, that is 25 degrees unless the problem says otherwise, so divided by 298 Kelvin. If you do a unit check, you will find that they all cancel out, and we get K is equal to 5.8 times 10 to the 29th. Many redox reactions that are spontaneous have very large K values. Alrighty, here's another problem. Calculate K for AgCl solid forming Ag plus Cl minus. This is actually KSP we're calculating. So I will let you do this problem by yourself. So when you're done with this video, go back and do that problem, covering up the solution. You're going to be finding the two half reactions that are relevant in the standard reduction potential table, and just follow through finding E naught and then using the equation K is equal to E to the NF E naught over RT. So come back and do that later. Alrighty, next we get into the Nernst equation, which is the one that we need to use when we are after the potential at conditions that are not standard. So far we've worked at standard conditions. So those are 1 molar concentrations, 1 atmosphere pressure, usually 298 Kelvin, but sometimes we're not at standard conditions. Now we'll look at the dependence of the potential on concentration and pressure. So in chapter 17, we had delta G is equal to delta G naught plus RT ln of Q. So as a reminder, this would give you the potential at whatever our concentrations are that we're starting with. So from those initial concentrations and all the stoichiometries involved in the reaction, we would calculate Q, and that RT ln of Q, recall that's the non-standard conditions correction term. Delta G naught is standard conditions. Okay, from this chapter, we have delta G is equal to minus NFE, and delta G naught is equal to minus NF E naught. That is to say, delta G and E go together, just as delta G naught and E naught go together, where the naught just is standard conditions. Alrighty, so we have delta G equals delta G naught plus RT ln of Q, which is negative NFE equals negative NFE naught plus RT ln of Q. Solving just for the potentials, we have the potential is equal to the potential at standard conditions minus RT over NF ln of Q. This is called the Nernst equation, and we use it when we don't have standard conditions. Another way of saying that Q is not 1. Whenever we have standard conditions, no matter the stoichiometries involved, we always have Q equals to 1. So the potentials involved, E and E naught, they differ by the RT over NF ln of Q factor, the non-standard correction factor. Calculate the potential at 25 degrees for a Daniell cell where the zinc 2 plus concentration is 1.99 molar and the copper 2 plus concentration is 0.010 molar. E naught, that is standard conditions, potential is 1.10 volts. Also, before we do this, should the potential under these conditions be greater or less than 1.10 volts? So let's look at the reaction. The overall reaction for the Daniell cell is copper 2 plus zinc yielding copper plus zinc 2 plus. And if we have standard conditions, we have 1 molar copper 2 plus and 1 molar zinc 2 plus. Well, imagine now we have much less copper 2 plus and much more zinc 2 plus. You could picture this as the reaction has run for a while. So we expect the potential to be less than 1.10 volts. It's like it's gone a while. Our battery is running down. So Q is the zinc 2 plus concentration over the copper 2 plus concentration, which is 1.99 molar over 0.010 molar, or 199. Our Nernst equation is E equals E naught minus RT over NF ln of Q. Putting in our terms, we have E equals 1.10 volts minus 8.314 joules per mole Kelvin times 298 Kelvin divided by 2 moles of electrons per moles of reaction divided by 96485 coulombs per mole of electrons. If you look at units, you see they all cancel out. No, I'm wrong. We end up with joules per coulomb, which is volt on for all those units, times ln of 199. So we're subtracting that from 1.10 volts, and we get that the potential is 1.03 volts, lower just as we expected. We can measure the potential of a cell with a voltmeter. Then, using Nernst equation, we can determine concentrations of the substances in our cell. So let's say we have this reaction here, copper 2 plus 2 Ag solid plus 2 Cl minus yielding copper solid plus 2 AgCl solid. And we're given the potential at standard conditions to be 0.10 volts. Calculate the copper 2 plus concentration when the potential has dropped to 0.070 volts. The temperature is 298 Kelvin and the Cl minus concentration is held at 1.10 molar. Okay, so we have our Nernst equation. E equals E naught minus RT over NF ln of Q. If we did the algebra and rearranged that equation to solve for Q, which I'm going to leave for you to do on your own, we have Q is equal to E to the E naught minus E, quantity, times NF over RT. Putting in our terms, we have Q is equal to E to the 0.12 minus 0.070 volts times 2 moles of electrons per mole of reaction times 96485 coulombs per mole of electrons divided by 8.314 moles per Kelvin, 8.314 joules per mole Kelvin divided by 298 Kelvin. We end up with Q equaling 49.12. And Q, if we look back at our reaction, Q is equal to 1 over copper 2 plus concentration times Cl minus concentration squared. Our unknown is copper 2 plus concentration, so we solve for that, and we get 1 over Q over Cl minus concentration squared. Putting in our numbers, we have copper 2 plus is equal to 1 over 49.12 over 1 squared, or copper 2 plus concentration is 0.020 molar. So go through that problem again by yourself. Make sure that you could work through it by yourself. Since delta G is equal to minus NFE, and delta G is equal to delta H minus T delta S, that's from last chapter, we have, by equating them, minus NFE from this chapter equals delta H minus TS from minus T delta S from last chapter. This equation shows the temperature dependence of E. Solving for E, we have E is equal to minus delta H over NF plus T delta S over NF. For a given, okay, so here's an example. Let's say in a particular redox reaction, we're told that both delta H and delta S are positive. Can the reaction be spontaneous? If so, which part of it, the delta H part or the delta S part, favors spontaneity? Also, how does the potential vary with temperature in this particular cell, in this particular reaction? Alrighty, so let's go back to delta H and delta S. If they're both positive, then of those two terms, delta H is positive. That means it's an endothermic reaction. Spontaneity is not it does not favor spontaneity, but delta S being positive is favorable. So the delta H term unfavorable, the delta S term favorable. Looking at our equation, E equals negative delta H over NF plus T delta S over NF. If we want to enhance the delta S part, then we want high temperatures. So we would say that E, the potential, would become larger as the temperature goes up in this situation. And the delta S term is the one that is favoring spontaneity. Okay, our last section is on the electrolytic cell. That's the other type of electrochemical cell. So it's the one that is used to produce chemical change. It's used to make chemicals using electrical energy. So basically using a battery to make chemicals that we want. The process using an electrolytic cell is called electrolysis, and it involves redox reactions, or at least the overall reaction being not spontaneous. Delta G is greater than 0. Energy must be supplied to make the reaction go. Okay, so delta G is greater than 0. The potential is going to be less than 0. Uh, in that top couple of sentences, I'm repeating what we just talked about. An electrolytic cell is an electrochemical cell where electricity is used to bring about an otherwise non-spontaneous chemical reaction. The cell is used to make chemicals. Delta G is greater than 0. The potential is less than 0. So much of what we have discussed with respect to galvanic cells applies to electrolytic cells. Three differences are: the two electrodes usually share the same compartment, and the anode is the positive terminal, the cathode the negative terminal. The anode is still where oxidation occurs, the cathode is still where reduction occurs. A single electrolyte is usually used, that is, we don't separate the compartments, and the conditions are usually very far from standard. Not 1 atmosphere, not 1 molar concentrations. Okay, so we'll look at an electrolysis reaction where we're making magnesium metal from MgCl2. So we need an electrolytic cell. The power supply drives electrons through the external wire, forcing oxidation and reduction to occur. So our overall reaction is molten MgCl2, so MgCl2 liquid, yielding Mg liquid plus Cl2 gas. The potential at standard conditions, at least, is negative 3.73 volts, so definitely not spontaneous. Now, indeed, magnesium chloride is found as a solid in nature. It's a solid at room temperature. So is the metal that magnesium at room temperature. But in this electrolytic cell, we are doing it in the liquid phase. We're making it molten. We're heating it a lot so that it's able to, the ions are able to move about. Okay, so there is the diagram of our setup of our cell. So we have just one compartment. We have two different electrodes. The electrodes are both, in this case, platinum, because otherwise we don't have any solid metal involved. So the anode, the oxidation reaction is occurring on the left side, the cathode reaction on the right side. Now, we are making electrons, we're forcing electrons to go away from we're forcing the oxidation half reaction. And if we take a battery, which is that rectangular box at the top with its two electrodes, the positive terminal and the negative terminal, what we do is we hook up the positive terminal of the battery to what we want to have as the anode side. Now, since the positive terminal has a positive charge, that causes Cl minus to be attracted from the molten magnesium chloride solution to that terminal, to that anode. And it then gives up its electrons because they're wanting to go to the positive terminal of the battery. They're then transferred through the battery and they are coming out. Notice that that's the negative terminal of the battery. The electrons being negatively charged are wanting now to get away from it, so they are going to the cathode electrode, and the magnesium 2 plus from the molten magnesium chloride solution is attracted to those negative electrons, so it's going over there and it's taking on electrons to give us the reaction Mg2 plus 2 electrons yielding Mg liquid, in this case, Mg the atoms. I give a little info about melting points. This process would have to be done at a temperature greater than, looks like 922 degrees Celsius to keep everything molten. Platinum has a melting point well over that, so using that metal is fine. So down at the bottom we have, since the anode is an extension of the positive terminal of the battery, it too is positive and Cl minus is attracted to it. Since the cathode is an extension of the negative terminal of the battery, it too is negative and Mg2 plus is attracted to it. Cl2 is produced at the anode and magnesium metal is produced at the cathode. Current supplied to the cell forces the flow of electrons in one direction, so that's done with the battery. It comes from a DC source, not an AC source, and it could come from like a 9-volt battery, for example. The anode of the battery is the source of electrons that enter the electrolytic cell and bring about reduction at the cathode of the electrolytic cell. Let's say the conditions of the Daniell cell, the copper zinc cell, has a potential greater than that needed to drive the magnesium chloride electrolytic cell. What I'm saying there is we're going to use the Daniell cell as a battery to drive this magnesium chloride electrolytic cell. So here's how we'd set it up. Okay, so the battery is shown on the left side. We have the zinc and copper separate compartments. We have the salt bridge between them. We have the anode, the zinc anode. We have the copper cathode. All that is over on the left side. You see what the two half reactions are. You see electrons going from the zinc metal up through the anode over to what it's hooked up to the cathode in our electrolytic cell. Our electrolytic cell is on the right side. It's one big compartment. Okay, going back to our battery, we have the copper electrode on the right side. Electrons are wanting to go in the copper electrode to copper 2 plus to form copper the metal. So that's that spontaneous process. And of course the salt bridge keeps the two compartment solutions neutral. Alrighty, so in our battery, electrons are going from the anode away, and then the electrons are wanting to go to the cathode of our battery. Notice the signs of our battery electrodes: anode negative, cathode positive. Okay, so we hook up the anode of our battery to the cathode of our electrolytic cell. The anode of our battery, negative sign, so the cathode of our battery, of the cathode of our electrolytic cell, negative. We hook up the electrode of our battery with its positive sign to the anode of our electrolytic cell, and those two therefore share the same charge, which is positive, as established by the battery. Alrighty, so you see electrons going from the battery anode over to the cathode, and those electrons are causing Mg2 plus to be oxidized to, or reduced rather, to Mg. The electrons are being forced away from the anode of the electrolytic cell to the battery cathode, and that means that the Cl minus is attracted to the plus of the anode, the electrolytic anode, and we're getting that oxidation half reaction. So definitely take a good look at that diagram so that it makes sense to you. A typical electrolytic cell calculation is done with dimensional analysis. Electron flow is measured via current in amps, where current, I, is equal to charge per time, or we have 1 amp is equal to 1 coulomb per second. Calculate the time required to plate out 1 kilogram of magnesium from an Mg2 plus solution with a current of 100 amps. Okay, so our reaction of interest here is Mg2 plus 2 electrons yielding Mg. So we have 1 mole of magnesium, 2 moles of electrons, giving us 1 mole of Mg, the atom. Okay, so we go from the 1 kilogram of magnesium to grams of it, so we have 1,000 grams. Now we have to go to moles of magnesium, because notice that we know the amount of moles of electrons involved in this process per mole of magnesium. So that's step one, is to convert the grams into moles. And now once we have moles of magnesium, we know that 1 mole of magnesium corresponds to 2 moles of electrons. Now we have moles of electrons. Well, charge is found using Faraday's constant. We know that in 1 mole of electrons, we have 96485 coulombs involved. So now we have moles of electrons canceling out. Now we have coulombs. Well, we have a current of a certain amount of coulombs per second, 100 coulombs per second. So that's our last step. So we write then the second over the 100 coulombs. We have coulombs canceling out. So the time required is 80,000 seconds, or 20 hours. Notice we did that all by dimensional analysis, but we had to start with realizing a mole of magnesium corresponds to 2 moles of electrons, because that was key to the conversion between the amount of magnesium we have and the amount of electrons involved. And then we could get into coulombs, and we could use the current to get time. So that would be another good problem for you to look at later. Here's another problem. Aluminum metal is produced commercially by the electrolysis of Al2O3. That's how it's found in nature. What mass of aluminum can be produced in 2 hours, 2.0 hours, with a current of 1.0 million amps? Alrighty, so this is dimensional analysis. The order we need to follow just depends upon what information we're given in the problem and where we're going. Alrighty, so we're going to go from our 2.0 hours to seconds, so 3,600 seconds per hour. And then we want to get into coulombs, because eventually we're going to go from coulombs to moles of electrons, from moles of electrons to moles of aluminum, and then finally to grams. Alrighty, so next step is using that 1.0 million amps, which is 1.0 times 10 to the 6th coulombs per second. So that's next. Okay, now that's coulombs. Now to go from coulombs to moles of electrons, we use Faraday's constant. Now we're looking back at our reaction, and for every mole of aluminum, we have 3 moles of electrons. And then finally, we want grams, so we just use the molar mass of aluminum, 26.98 grams per mole. And we get 670,000 grams, or 670 kilograms. So the next ones are just some diagrams for your interest. Electrolysis of water, that's breaking water into O2 and H2. And we have the diagram here, the cell diagram, where the anode is what's on the left side, the cathode is what's on the right side. Anode, the oxidation is occurring there. That would be 2 H2O yielding O2 plus H plus 4 electrons. That's occurring at the anode. At the cathode, we have reduction occurring. That would be 4 H2O plus 2 electrons yielding 2 H2 plus 4 OH minus. And the overall reaction is 2 H2O yielding O2 plus 2 H2. Notice that in our overall reaction, we have twice the amount of H2 produced as O2, and we can also see that. That is, the H2 is the one produced at the cathode. That volume is about twice as big as the volume in the anode, which is showing the production of O2. Also, if we had an indicator that would indicate acid base, we see that on the anode side, we're producing H+, so acidic. On the cathode side, we're producing OH-, so basic. So right around where the reaction is occurring, if there were some indicator that would show the color to indicate acidic, basic, we would be able to see that. Here is the reaction showing how platinum is plated on to teapots, to spoons, and so on. So it is being forced to happen, and we have the piece of silver in the compartment. That's going to be the source of the silver that is plated onto the spoon. So it's being oxidized. Electrons are being forced in the other direction, and then that oxidized silver is attracted to the cathode, and it is then taking on an electron and being plated on. Alrighty, so those are our notes for chapter 18. So now go over those again as often as you need to make sense. Read over the handout as well on your own, and do the assigned homework problems in the chapter, as well as read through the chapter. The quiz chapter 18 will eventually open, and when it's open, make sure you take care of that. And we have, of course, some experimental work, the pre-lab, and we have some exercise work. So I will be reminding you usually on Mondays of what's due that week, and also you can always go into Canvas and check on due dates to see what's due.